alkyl halides and alcohols both represent important organic functional groups. Both of these functional groups share several key characteristics, including they share some common reactivity. The reaction I'm going to look at in today's video is nucleophilic substitution. So if we look at the structure of an alkyl halide or an alcohol, so we have our alcohol here on the left. Here's a simple alkyl halide on the right. With all of our alkyl halides and our alcohols, we have an electronegative atom, our oxygen or our halogen, which is attached to a carbon. Right? This results in a dipole towards our electronegative atom from that carbon. So we end up with a partial negative atom and a partial positive carbon in both our alcohol and our alkyl halide. The end result of this is that we have a somewhat nucleophilic alcohol or alkyl halide. So it's electron rich. That means it wants to react with those electrons. And on the other side, we have our carbon, which is somewhat electrophilic. Our carbon has a partial positive charge, indicating that lower electron density. Again, our electrophilic site and our nucleophilic site are going to represent areas of reactivity for our molecule. Now, in our nucleophilic substitution reaction, the first nucleophilic substitution reaction that we'll look at, we can react between a hydrogen halide and an alcohol to form an alkyl halide. Our generic nucleophilic substitution reaction between a hydrogen halide and an alcohol is as follows. So our alcohol will react with our hydrogen halide. Again, in this case, our R is representing any generic carbon-based chain. Our X here is representing any halogen. Right? So we have our hydrogen halide. We react with our alcohol, and we're forming, of course, water over here on the right, and an alkyl halide. We refer to this as a nucleophilic substitution reaction because we're taking our halogen nucleophile and we are reacting with our alcohol nucleophile, and we're essentially changing the positions of these two groups. Right? So in our product here, we have our oxygen nucleophile in water. So we took our hydrogen from the hydrogen halide, and now here our halogen is with our alkene group from our original alcohol. So basically trading which nucleophile is attached to which substituent. To understand the substitution reaction, we need to know how our reaction happens. So for the first step of our reaction, so we're taking our initial reactants. We have our alcohol over here on the left and our hydrogen halide here on the right. Now, since our hydrogen halide is a strong acid, right, we have this hydrogen with a relatively weak bond to our halide, and we have our alcohol here, which is nucleophilic and can act as a base. So our alcohol will act as a base. We'll attack that hydrogen with our lone pair of electrons, and our bromine can then take those extra electrons as it donates the hydrogen in this acid-base reaction. This will result in our protonated alcohol, or alkyl oxonium ion, where now, since we've used one of our lone pairs, we only have one lone pair on our oxygen, and we have a positive formal charge. On the other hand, since our bromine donated that proton, our bromine will now have 4 lone pairs, and we'll have a formal negative charge. Now, once we've protonated our our alcohol to create our alkyl-oxonium ion, we now have our oxygen that's electron deficient, right? So our oxygen is electronegative. It really wants to get more electrons. To do that, it's going to want to pull, again, our electrons away from our carbon, right? So we're trying to pull those electrons away. And we can actually end up pulling those electrons to our oxygen. So we can break this bond in our next step. This is a dissociation of our oxygen here from our alkyl-oxonium ion. We refer to this as a leaving group. Because since our oxygen is taking those electrons and breaking away from our carbon structure here, it's leaving our carbon structure, therefore it's acting as a leaving group. So if our oxygen takes those electrons, now we're going to end up with our water molecule. Remember, of course, this was one of our products of our reaction overall. This is good for our oxygen because now it has more electrons again, like it wants to. It doesn't want to have that positive charge. However, on the other hand, our carbon just lost 2 electrons, right? So if our carbon lost 2 electrons, that means we're now going to have a positive charge here for our carbon. This is what we call a carbocation. So we have a positive charge. We also only have 6 electrons, 2 each from our 3 bonds here for our other carbons. We have our 3 carbons that we're bonded to. We have our central carbon here in the middle. And since we only have 6 total electrons bonded to our central carbon, that means we're lacking our full octet, and our carbocation is going to be relatively unstable. So our carbocation is unhappy, right? It doesn't have the electrons that it would really like to have in order to have that stable full octet. Now, if we look at our components right here, so we have, of course, our oxygen here in water. It's quite happy, right? It has all the electrons that it wants. It's able to even pull some extra electrons from those hydrogens based on its polarity and high electronegativity. Our bromide ion over here has a lot of excess electrons, right? So we have a negative charge, and we have 4 pairs of our lone pair electrons. So that, of course, means that our bromide ion is a good nucleophile, right? It has high electron density. Our carbocation over here is an excellent electrophile, right? It has very low electron density. It really wants to gain electrons. Our bromide has those extra electrons, so it's very happy to provide those extra electrons to our carbocation. We use our curved arrow to show those electrons coming over from our bromide to attack our carbocation here. We're missing our extra electrons. And now at this point, those 2 electrons are going to form a new bond to our carbon. And we create our alkyl halide product. We have our alkyl halide. Of course, our water remains unchanged from the previous step. And now, of course, our overall reaction is complete. We've gone from our alcohol, and we took our nucleophile from the alcohol. This left as our leaving group after we protonated it, and eventually gained our hydrogen to become water. Our bromine, the nucleophile from our hydrogen halide, substituted onto our carbon chain to create our final alkyl halide. So again, we go from our hydrogen halide and our alcohol. Then we react to produce our final products of the water and our alkyl halide. This reaction occurs in 3 distinct steps. We have our first step here of protonation, where our strong acid hydrogen halide protonates our alcohol to form that alkyloxonium ion that has our water as a good leaving group here. Our oxygen with those 2 hydrogens that becomes water as it comes off. In our second step, we have our dissociation of that, what becomes our water from our alcohol to create the carbocation. And now in our third step, we have our association, where our nucleophilic bromide ion attacks our carbocation to create our final alkyl halide and water. So here we have our overview then of our first nucleophilic substitution reaction. So again, we're able to exchange our oxygen-based nucleophile from the alcohol with the halogen nucleophile from our hydrogen halide. In this case, of course, it's our bromine, to produce that final alkyl halide and our water. This particular mechanism that we show here with our protonation, dissociation, and association is called an SN1 mechanism. And we'll look at some other different examples of nucleophilic substitution mechanisms later. So this shows us how we can start to react between our different alcohols and alkyl halides. So we can use alcohols to form alkyl halides with the nucleophilic substitution reaction. We can also actually react our alkyl halide to form alcohols as well. We can use water. This would be a hydrolysis reaction. We can push this backward to produce our original product if we have an excess of water. So we'll look at other examples of nucleophilic substitution later, but this gives us a good introduction to our first nucleophilic substitution reaction.